Wow. Hi, everybody. Still pretty weak. Hello, everyone. Thank you. This isn't a classroom. We're going to have fun tonight, so I like to hear the cheers. As most of you who have been here before know the drill, we like to welcome back those who have been here in the past. How many of y'all have been to Astronomy on Tap in the past? All right, a good cohort. How many of you are here for from UTSA to support your professor and grad student colleague? Yeah, there we go. And how many of you are brand new to Astronomy on Tap? All right, welcome. That's excellent. We always like to make sure we're getting new people in. Hopefully y'all come back so next time you can raise your hand to the first question instead. So my name is Tracy Becker. I'm one of the organizers here with
Michael Velez.
Aaron DeLeon.
Samuel Hart.
and Adam and Brian are over in the corner. All right, so for those of you who haven't been here before, don't worry. We actually have on the very next slide an introduction to what we're all about before we get started on our awesome talks that we have for you this evening. So thanks again for coming.
All right, so what is Astronomy on Tap? Well, it's a worldwide phenomenon, as I like to say, as we have locations across the world. Most of them are here in the United States, but there's a lot in Europe and others as well. And actually, the Astronomy on Tap as a whole, just last month, celebrated its 10-year anniversary. And tonight, we are, this is, something's, okay, hello. Yeah, okay, we're good now. We are celebrating exactly 1 year of return to in-person events for our AOT here in San Antonio. So thank you all. Yes, thank you all for coming back. Before we left, we were filling up this room, and we're filling it up again, and we're really excited about it. And we hope to have more and more years of events moving forward. So what do we do here? What is the nuts and bolts? Well, we like to have fun. All of our talks are interesting. And they are interactive because you all will get to ask questions. Our television isn't working right now, but we'll make sure that you have the phone number to ask the questions to. And at the end, we will have trivia where everyone will have a chance to win some really cool prizes, including posters and stickers and NASA trading cards, which are a lot cooler than they sound, believe me. And moving forward, for those of you who have been here before, thank you for your continued support. But if you're new, or regardless, we have our social media so you can follow us. We'll post updates on what our next events are and photos from our previous events and whatnot, so you can keep track of us right there. And Sam will talk about tonight's event.
Hello. Okay, there we go. Hello, everybody. Today we have two excellent talks. They're actually different than what we normally do because both talks go outside of the solar system. Usually we stay inside. This time we're leaving. So it'll be a fun journey. First, we're going to have Dr. Lisa Shepard talk about astrophysical masers, or space lasers, as she calls them. We will then have a quick break, followed by Caleb Gamar talking about astronomy in the news. And finally, Erica Dykes, UTSA graduate student, will be talking about how we detect and characterize exoplanets. So very interesting stuff. And without further ado, I will hand the microphone to Tracy to introduce our first speaker. Thank you.
All right, so before we get started, I did actually mean to ask one other question. For those of you who are new, how many of you knew that folks here in San Antonio at UTSA and at the Southwest Research Institute are currently actively working on space exploration and science and studying all of these cool places? Couple hands. You can shout. Did you know about it? Yeah, okay. How many of you didn't know? Raise your hand. A couple people, yeah. So some really cool stuff. In addition to the really cool talks we're going to hear about today, I also wanted to give a little shout out to, we actually have a team working on the Juno mission. How many of you have heard of the Juno mission in the past? All right. That little table corner over there, some Juno reps. So hello, Juno team. Thanks for coming. All right, and without further ado, I'm very excited to introduce Dr. Lisa Shepard. Dr. Shepard has been interested in space since her little brother told her that the moon was made of cheese. Her expertise in the field has since grown. She ended up getting a bachelor's degree in physics from the University of Arkansas, and then gone on to get a PhD in physics, astrophysics from Mizzou. How many Mizzou folks here? I know there's a couple, yeah. And then she is now a part of the UTSA Roadrunners tribe. She is an associate professor of instruction at UTSA, and mostly studying stardust and space lasers and dying stars, and we're going to get to hear all about that. And one cool tidbit was that last summer she went to my favorite observatory, the Arecibo Observatory, to learn more about doing radio observations in addition to her typical studies in the infrared. So without further ado, I present Dr. Shepard. Thank you, Jason.
My drinking word today is energy.
A reminder, or if you're new, what the drinking word is as many people who have been here, thank you for the gusto. When she says energy, you'll take your drink and say, woo, and take a sip. And she will try her best not to say it too often, but you got to keep up. No. But also be responsible.
Down is the way to go. All right, be prepared to drink frequently. All right, so tonight I'm going to talk about space lasers, which is my cool way of saying astrophysical masers. And in order for you to understand what a maser is, I need to talk about how a laser works, because a maser is just a laser that operates at microwave wavelengths. And in order for you to know about lasers, I have to start with talking about atoms and electrons. So if an atom absorbs a photon, then an electron orbiting that atom is going to go to a higher energy level. But electrons don't want to be at higher states. They want to go down to lower states, and when they do, they release a photon of light. And if it does this naturally, it's called spontaneous emission. And if we have an atom already in an excited state, and we have a photon of a certain wavelength fired at that, it will absorb that photon and very quickly emit 2 photons of that wavelength, and we'll have our electron or our atom go down to a lower energy state. And this is known as stimulated emission. So naturally is spontaneous, and if we fire a photon at it, we've got the stimulated emission. And the acronym LASER stands for light amplification by the stimulated emission of radiation. We have, what did I do? What did I do? What did you do? Okay. All right, here we go. Lasers. Oh no, I didn't do it. Max. Are you going to have to do it manually?
Yeah, I'll try it.
One more. Okay, okay. All right, hold on. All right, for a laser to work, we need two things to happen. We have to have that stimulated emission that I just talked about, and we also need population inversion. So normally for a material, the electrons in it are going to be at a lower energy level. There's going to be more of them at a lower level than a higher level, and that's the natural state. But if we have more electrons at a higher level, then we say it has population inversion. So a laser requires both population inversion and stimulated emission. A laser requires a gain medium to operate, and usually this is a gas that the radiation passes through, but it can be any state of matter that is put into an excited state by an external energy source. So we have excited atoms or molecules in our gain medium, and we have radiation passing through it, and we also have them inside of a resonant cavity, so that our radiation can pass through back and forth several times. Usually, this resonant cavity is composed of mirrors, and one of the mirrors will be slightly transparent so that our light can escape. Next. All right, so some laser properties. First of all, the gain of the material. Go ahead, Tracy. All right, the gain or the amplification is exponentially related to the length of the resonant cavity. So normally with our lasers, the radiation passes through back and forth in the resonant cavity. That's not always required. You could have one pass for this to work. Another property of it, Tracy, is that the laser light is coherent. And that just means that all of our light is of the same wavelength and in the same phase. And the other property of it is that laser light is monochromatic, or one color, and it's also collimated, or it's parallel for over a very long path. All right, so the acronym MASER is generally understood to stand for microwave amplification by the stimulated emission of radiation. Although Charles Hart Townes, pictured here with his ammonia maser, proposed that the word molecule be used for the M instead, because it is the energy transitions of molecules which are responsible for the different frequencies that we observe. So Charles Townes, he actually built the first maser. Go ahead and put one more. In 1953, he worked along with his students, so shout out to the students here tonight. And this was based on a theoretical paper by Joseph Weber written in 1951. And actually, so people always think of lasers as being the first type of this that was built, but actually the first functional optical laser was not built until 1960. So the maser was built first, and when they built an optical laser, they referred to it as an optical maser. Now, not only can masers be created in the laboratory, but they can also exist naturally in space. So when a maser was created in the lab, they did not know these because it exists in space. And what an astrophysical maser is, it's a region of gas which amplifies microwave radiation through stimulated emission. So similar to a laboratory maser, you must have stimulated emission and population inversion for an astrophysical maser to exist. Another thing about astrophysical masers is that radiation from the star travels through the gain medium in a single pass, and again, the amounts of amplification or gain is related to the length of the path that it goes through. So a major difference between masers in space and a laboratory maser is that you can have a resonant cavity in a laboratory maser, but in space you only get one pass for the radiation through the material. That's it. And for that reason, they tend to be weak and difficult to detect. So the first astrophysical maser was detected in 1965, and people had observed emission lines at a frequency of 1665 megahertz, and at the time it wasn't really believed that these molecules could exist in space. So when it was discovered, people didn't know what it was, and astronomers gave it the very scientific name of mysterium. Later on, that spectral line was identified as a transition of the OH, or the hydroxyl molecule. And an explanation of the signal was given by R.D. Davies in 1967. Since then, many more transitions have been found, and many more amazing molecules have been discovered. And right now, the complete list of known molecules for astrophysical masers are listed here. I'm not going to go through them, just want to point out that there's a lot of types of them. And masers can exist in many different astrophysical environments, and the most common astrophysical environment for astrophysical masers to be found in is in star-forming regions. And this consists of young stellar objects and hydrogen-2 regions embedded within molecular clouds. So you need to have some type of energy source. That could be a star, but it also happens in these molecular clouds because you have enough material there, the density is high enough that you have collisions between the molecules, and you can have shock waves traveling through the molecular cloud. So that is how we can have these astrophysical masers in these environments. Masers have also been found to exist around comets. And for example, Comet Hale-Bopp, pictured here, was observed to have a hydroxyl maser. And the reason why we observe hydroxyl masers is because water, or H2O, exists out in space, and ultraviolet radiation breaks that molecule down into OH. And then, masers have also been found in the atmospheres of giant planets and stars, including stars that host exoplanets. And go back. So here we have, I have an image of Comet Shoemaker-Levy 9. When it impacted into Jupiter, a water maser was observed during that impact. So that was in the atmosphere of Jupiter. All right. Masers are also found around late-type stars and supernova remnants. So first of all, for supernova remnants, it makes sense that you have a lot of energy spreading out into space into this dense region around it. So you have masers often observed around supernova remnants. And then of course here for late-type stars, this is a variable star known as TX-CAM. And the red disk there shows the size of the star itself, and then the bright spots around it are showing the silicon monoxide lasers in space around it. Now the thing about variable stars, well, because they are variable, the amounts of material in space around them is changing, and that means our masers are also changing, which I have on an animation here for the next slide. So this is a movie made of silicon monoxide masers around that same star, TXCAM, which is a variable star. And you can see that because of our star's variability in pulsations and material out in space, that we are seeing the maser strength changing. So this means it's difficult to detect. Maybe if you're doing an observation at the wrong time, you're not going to detect the presence of the species of maser. And then there's another type of maser which has a lot of energy. And this is known as a mega maser. So we can see in distant galaxies these regions around the active nuclei of these galaxies. Maybe it's the accretion disk around a black hole, but there are these powerful mega masers which are like 1 million times brighter than the ones we're observing in our own galaxy. And typically, they're the size of our solar system or larger. So the image up here on the left is of the galaxy M106, and that's located about 23 million light years away from us. And it's shown in red because the image is made in the hydrogen alpha lines, which is the red part of the spectrum of hydrogen. And then from the insert, which is shown here on the right, this is an artistic rendition of that mega maser area near the center of this galaxy. And from looking at it, we can see the rotation of this dust and gas disk. So the blue part means that it's moving toward us, and the red is moving away from us. The green is no motion relative to our line of sight, and all of those white spots on there represent water masers. So masers exist in many astrophysical environments, and by observing them, we can tell things that we can't see because these environments are located in areas where we have very thick gas and dust, and we can't see them optically, but the masers allow us to look through that and make observations for that area. For example, by knowing the type of maser species that are there, that tells us a little bit about the composition of that area. If it's an area that is moving, we can tell the velocity because of how much it's redshifted or blue shifted. We can tell how much, what's the temperature or density of that area. And that's something that we can tell by, some of the things we can tell by observing astrophysical masers. So basically, they can exist naturally in space as long as the conditions are right with the proper density and energy of material. And that's all for me. Thank you.
All right, next up we got some questions, and we're going to decide how we're going to do it. All right, Tracy's going to put up a phone number. Everybody text that phone number for some questions. I got one question already. I'm going to hold this lower while we work on getting that one. All right, first question. What was the exposure time of the maser movie of the variable star?
Yeah, I don't have that memorized.
All right,
No,
Sam wants a ballpark.
It's actually over, I think it was over a few days' time. So that's the
Okay.
ballpark. Yeah, the frames were taken a few minutes apart over a few days' time.
Cool. All right. Next question. Waiting for some of them. Okay. How do you detect or measure the masers? What kind of telescope?
Well, what happens is, so we say that they're microwave wavelengths, but actually a lot of them are detected in radio wavelengths. And what we see is because we have this bright line due to the electrons jumping down the energy levels, right? So we see a bright peak in the spectrum at certain frequencies or wavelengths, and that corresponds to the transitions in the molecules for those masers. So we see just very bright lines at certain wavelengths, and that's how we can tell that there are masers there. Not only that, but they usually don't have just one transition. There's multiple ones, for example, corresponding to water. And then we can say, oh, it has these bright spots. There must be water there.
Cool. All right. Next question. Did the intro say you went to the Arab-Seer Observatory in Puerto Rico last summer? I thought it was decommissioned.
Not yet. Maybe soon. So yeah, the big dish has collapsed, but they still have other facilities there. When I was there, I used the 12-meter dish. They have lighter facilities there to study particles in the atmosphere. So yeah, there's still active research going there, and there was a proposal put forth. I don't know if it was asking for funding from the National Science Foundation, but they wanted to build a new dish there. It looks like that's not happening. There's people working on it and talking to the government, going to Congress, trying to, Tracy wants to interrupt.
Yeah.
No, if you want to support the Arecibo Observatory, write to your local congressperson and senator, and we are still actively trying to support returning science to the observatory, or continuing it past August, which is when it will currently end. So only Congress has the power at this point to make it happen. So that's true.
All right. One more question? Two more? We'll find out. Okay. Are all of the masers unidirectional, or do they radiate emission in all directions? Do they happen just to be pointed at us?
Oh, they're all directions. But yeah, we're only going to observe things that are pointed at us. Like the movie that I showed, you could see from where we can observe around that star. They're all around that star, but yes, they're actually are in all directions generally, yeah.
All right. Let's do... Okay, last question. So the megamasers, do they have enough energy to destroy things in their path, or are they more strong radio sources?
There are more strong radio sources, yes, just very bright light. I think if you've got a mega maser in your region, you've got other problems to worry about. Yeah, not the frequencies of the light.
So more
or
of
how
a
much there
telltale
is.
sign.
Yes.
All right. Yeah, all right. So we're going to take a break now. All right. So let's thank our speaker, Dr. Lisa Shepard.
Thank you.
Yeah, so we're going to take a break, come back at 7:40, 8 minutes. Please don't crowd the bar. We ask that you
else. Just, you could finish up your conversations. It's okay. All right. I would love to present astronomy in the news, but I suck at presenting. So instead, our expert Cosmosphere alumni, Caleb Gamar, will be presenting. Give it up for Caleb.
All right, well, good evening, everyone, once again. Do I still have that kind of echoey effect over there? Yeah, I do. All right. As long as I have, okay, yeah. I was going to say, if I still have the echo, I should start singing Heartbreak Hotel. If you ever listen to that recording, it has a really great echo effect on it. Anyway, so, astronomy news for this month. We'll go ahead and start off with that. So, for the May skies, if you go outside around 10 o'clock p.m., this is what the sky will look like. It is a perfect springtime sky because we are indeed in the spring season. You will notice that the constellation of Leo the Lion is straight overhead. The constellation of Ursa Major, which contains the Big Dipper, is not too far above it. Good guide to going around and seeing things in the springtime sky. Follow the arc of the Dipper to the bright star Arcturus, spike down to Spica, follow the front two stars of the Dipper on down to Regulus, which forms the heart of Leo the Lion. So yes, indeed. So that is the way of kind of finding your way around the springtime sky. Now, there are a couple of planets visible this month in the evening sky. Venus is very, very well placed and very bright. So always look over toward the east at sunset and even a little while after, and you will see a very, very bright star-like object over there. That is the planet Venus. Look at it with the telescope, and you will actually see something that looks like a quarter-phase moon, without all the surface details, of course, through the field of view. Venus is one of only two planets in our solar system that we can see both the day and nighttime sides from the planet Earth significantly, and that's because Mercury, the other one, and Venus are on the inside of our orbit around the sun. Now, if you have a very large pair of binoculars and a very, very dark nighttime sky, or a telescope for that matter, go out and look around that region of the sky right there, right at the back end of Leo the Lion. And that, and that is where you will find the nearest large galaxy cluster to us, the Virgo galaxy cluster. It's on average about 65 million light years away, so you're looking at it as it appeared about 65 million years ago, about the time that the dinosaurs roamed the Earth. And when you look at that region, you will see a number of little gray fuzzy spots through that large pair of binoculars under a very dark sky. But again, it is an observing challenge, so you will have to look closely. Big news for anyone in here associated with the JUICE mission. There we go, all right, yeah. JUICE launched, yes. Launched on April 14th. It sent back a number of images of the Earth on its way out. That's one of the really beautiful images of the Earth on the way out. For the most part, so far so good. There is one instrument that is having some issues. It's one that has a large antenna that still needs to be deployed. Nonetheless, they're working through the problems. Again, really great launch, and hopefully, in a very long time, 2031, July of 2031, it will arrive at Jupiter and start sending back data about, of course, the Jupiter system as a whole, but certainly the large moon, Ganymede. Now, another rocket launch had a little different story. So, the SpaceX Starship accomplished its first all-up launch, I guess you can say, the entire stack launching. Now, the thing is, though, it worked until it didn't. There was an earth-shattering kaboom. Yes, you're right. First stage actually worked very well, and then about 4 minutes in, stage separation as planned did not happen, and of course the abort button had to be pressed and the destruct mechanism went off. But nonetheless, though, congratulations and wishes for further better progress to SpaceX on the Starship program. Now, here's a rather interesting story I came across, one you might not have heard about. A balloon-borne telescope program called SuperBit. NASA is involved in this program. This particular balloon was launched from New Zealand. It's at an altitude of about 130,000 feet, quite a ways up there, and it is circling over the Antarctic. It actually just a few days ago made its first entire pass around the Antarctic, and as that balloon it goes through this mission in that region of the atmosphere, it carries on board this telescope that's sending back, the telescope's right there, that's sending back these really, really beautiful images of space objects. In this case, you see the Tarantula Nebula and the Antenna Galaxy there, and I was really fascinated. Yes? What wavelength? Visible. Those are visible. And it does some infrared too, which is why, of course, you want that high altitude. It does have some infrared capability as well. So a couple of exoplanet findings. One, the James Webb Space Telescope did conduct some observations of an exoplanet, or at least an exoplanetary system, I should say, and possibly, and I say possibly for a reason, possibly found traces of water vapor in the planet's atmosphere. Now the problem is, if you look at this, you have a couple of models. One is a model of the stellar atmosphere of the star it's around, and the other one is a model of the planetary atmosphere. They don't diverge much toward the region that Webb observed, so it's not yet clear whether that was a detection of planetary water or a detection of the star's own atmosphere having some significant compounds in it related. Nonetheless, the planetary system, GJ486b, it's about 26 light years away, so a pretty close stellar object, and of course a planet going around it as well. And then just announced today, astronomers also observed a star engulfing a Jupiter-sized planet. Yes, it actually happened just a while back. There was a transient infrared light emission from a stellar object, and this implied, after analysis, that the star actually engulfed a large Jupiter-sized planet around it. Probably what will happen to our own Earth about 5 billion years from now, so get ready. It's going to get real hot a long time down the road. So, yeah, more beer. So, new radio imagery of the M87 black hole. So, many of you probably remember a number of years ago, 2019, spring of 2019, really big deal. First image of the event horizon region around a black hole. Now, I was at the center of the galaxy M87, about 55 million light years away. And you can see it in this image here. Well, there has been a further development in imagery of this black hole. If you look at the radio wavelength around this black hole, there actually is the observation here of a couple of jets of material away. Of course, it's been well known there's jets of material away, but this is the first image that reveals both the shadow of the black hole and the energetic jet at the same time. This was taken using a global millimeter, very large baseline array. It's basically a worldwide combination of radio telescopes that are able to gain this imagery. And then the original image from the Event Horizon Telescope project, another similar worldwide linkage of radio telescopes, that imagery has been enhanced very recently using machine learning algorithms to give a little higher resolution version of the Event Horizon image here. So very interesting work involving this particular black hole. Do not miss my continual final notification. The annular solar eclipse coming up on October 14th. Pretty quickly here. Get those eclipse glasses if you haven't already, because they'll start going away really fast here down the road. And then, of course, the total solar eclipse on April 8th of next year. So we are just a little under a year away from that total solar eclipse Both of those will be very well visible from the San Antonio area. This Friday, weather permitting, and I say weather permitting for good reason, we have a First Friday observing up at the University of Texas San Antonio Observatory, the Correspond Junior Observatory. So definitely keep that in mind, and I hope to see many of you out there if we actually do it. UTSA main campus, yep. And then I'm going to close out just with these two really cool images, something I found in looking for these stories. The one on the left-hand side is of Mars and its moon Deimos as imaged by the United Arab Emirates HOPE mission, which is orbiting around Mars right now. And then the one on the left is the Hubble Deep Field, but instead imaged by the JWST. So really pretty images, and that's where I'll leave off. Thank you very much.
Thank you, Caleb. Some of y'all texted in questions. If you have questions for Caleb, I'm sure he doesn't mind if you ask him, right? You know, people just walk right up to him and ask him. He's a personable guy, so get to know him. Our next speaker of the night is a fellow graduate student at UTSA, Erica Dykes, and a little intro here. Erica is originally from North Carolina. She received her BS in physics from the University of Missouri in Columbia back in 2020. What a time to get a BS. She's currently a PhD student at UTSA working under Dr. Thane Curie, with her main research interest being planet formation and exoplanet detection, which is what she'll be talking about tonight. And she currently works on high-contrast imaging of protoplanetary disks in the near-infrared. So everyone, please give it up for Erica Dykes. All right, and we're all dying to know, what is your drinking word? Uh-oh. The light's not on. I think it's out of battery. Yeah. She'll get this one. Your drinking word is?
Exoplanets.
Oh, bold. So exoplanets. All right, we're good to go.
Awesome. Thank you, Michael, for that introduction. So I'm going to start off, hopefully. All right, apparently none of this technology wants to cooperate with me today. Love this. Down? Okay, cool. Thank you. So I'm going to start off with a simple question for the audience. By a show of hands, how many of you are familiar with what an exoplanet is? All right, cool. A lot better than the last time I asked an audience what that was. So for those of you, so we're all on the same page, and so the people who are not familiar with the term know, an exoplanet is simply a planet that is not in our own solar system. So if it fits all the other working definitions of planet, and it is not gravitationally bound to our star, it qualifies as an exoplanet. Sorry in advance, please drink responsibly. All right, so another thing that I think is really important for context is how young the study of exoplanets actually is. So the first exoplanet was found in 1992. Sorry, I'll try to be a bit better about that. But it was found around PSR B1257 plus 12, which is a pulsar in the Virgo constellation, appropriately given the nickname of Lich, because pulsars are not fun places to be around. Definitely do not recommend trying to live on a planet around a pulsar. Now, the next important discovery for the field of exoplanets happened 3 years later, in 1995, when the first exoplanet Hey, man, they told me to pick a word. I picked a word. Was found around 51 Pegasi b, which was the first exoplanet, around a main sequence star, so a star like our sun that is still fusing hydrogen. And then, as of last year, we found our 5,000th planet. You're welcome. So this just goes to show how fast this field has grown in only 30 years. So, Oh boy, that slide was not supposed to be there. Cool. So I guess I'll talk about it regardless. But this is the current distribution of planet types that we have. As you can see, we have a pretty even distribution of gas giant super-Earths, Neptune-like planets, but we are very underrepresented in Earth-like terrestrial planets, and you'll see why here in a few minutes. So that just goes to the full question for this talk, which is how exactly do we find these objects? So the first one that I'm going to talk about is actually the one that I personally use, which is direct imaging. So direct imaging, the entire idea behind it is getting light directly from the planet, as the name suggests. And we have to correct for the atmosphere to be able to do that, which we do with something called extreme adaptive optics at this point, which basically just uses a mirror and some sensors to back out the light distortion that we get from the atmosphere. And then we also have to block the star's light, which we do with coronagraphs. And as you can see, if you look very closely, up in the lower right-hand side of the coronagraph image, there is actually a little planet there, which becomes much more evident when we further do post-processing, i.e. taking out more of the PSF of the star. So, because we can see the planet itself, we can actually make fun little GIFs like this of our data, which is showing Beta Pictoris b over the course of a number of years. And you can see that the planet is starting in the lower right-hand corner and traveling up behind the star, behind where the coronagraph is blocking out our data, and up to the left-hand side. And so, obviously, we can trace the path of these exoplanets as they go around their stars if we have enough time to observe them. So that means we get the orbital parameters, which are really important. And because the orbital parameters are primarily dictated by the relative masses, then we can also get the mass of the exoplanet. And again, because we're looking at the light from the planet itself, we can get spectral information, which means that we can get atmospheric composition information. We can also tell if it's a particularly cloudy object, because most of the objects that we find, actually all of the objects that we find with this method, are very large gaseous objects, either large Jovian planets or brown dwarfs, which are substellar objects. Now, the important thing to remember is that there are a few limitations with this, and they are pretty severe, which is why we have only found about 25-ish planets using this method. So the main one is that stars are very, very bright in comparison to any planet that you look at. And best case scenario, you're looking at putting a firefly right next to a really bright light bulb, walking about 20 kilometers away and trying to find the firefly. That's best case scenario. It only gets a lot harder from there. So, fun times. Because of that, or because of the coronagraph primarily, we also have to look at wide separated planets, which means planets that are tens of AUs, so 10 times further away from or from their stars than Earth is to our own. And that severely limits the population of planets that are accessible with this method, hence why we don't have very many of them. Now, the next one I'm going to talk about is gravitational microlensing, and it makes use of the fact that general relativity tells us that mass bends space. And so when you have a situation like the one shown in the figure here, where you have a background star, and then a planet hosting star comes in between, comes in between us and the background star, what you can get is a distortion of the space around the foreground star. That really help. That's not how that works, but okay. Thank you for the quick assist. Yeah. So when an exoplanet is around the star in between us and the background star, what we end up seeing is a graph like this, which what you're seeing here is a map of the light from a background star over the course of a number of days and the magnification of that background star. And what we see is there's a big brightening event from the star itself as the light is bent, or light that normally doesn't get to us gets bent towards us by the intervening masses, and a cute little secondary brightening event off to the right here, which corresponds with the planet itself. So again, this is a method where we never actually see the planet. We're just seeing the effect of the planet on the light of a very distant star. And because it's gravitationally based, we get the mass, and we can also potentially get the orbital distance, although that's a little bit harder to constrain. The major issues here become that these are random chance events. We can't point at a star and go, a gravitational event is going to happen here. Cool, let's watch it. Not how it works, unfortunately. The upside, though, is that this is not constrained to stellar mass objects. We can get what we call free-floating planets with this particular method. And that means that you don't need a star. This is the only method that we can use to find rogue planets, i.e. those are planets that have been ejected from their systems. So yeah, but unfortunately it's hard to confirm these because those kind of rogue planets and sometimes even the bound ones are very difficult to follow up with. They're very hard to see with other methods because they're much farther away, typically. So, next what I'm going to talk about is radial velocity. And this little animation will give you a little rundown on how this works. But generally, we're making use of something called the Doppler effect. You are all familiar with this, I promise. It's the effect you hear when an ambulance is coming towards you and then going away again. The pitch increases as it's coming towards you and lowers as you go away, and that is a Doppler shift. It's due to relative motion between you and the emission source. And the same thing happens with planets or stars out in the universe. So when an exoplanet is tugging gravitationally on a star, you get motion of the star around a center of mass, and if it's in the right alignment, in other words, in an edge-on system, then we can watch the star's light dance around and shift to redder wavelengths, bluer wavelengths, and back again. And that's characteristic of a planet. And so what we end up getting is a lovely graph like this one, which is actually the graph from the original paper for 51 Pegasi b. And what it shows is you get this sinusoidal wave of the radial velocities as that star is going around its center of mass with the planet. Cool. So that means it gives us mass, it gives us eccentricity, depending on how this particular sinusoidal wave is distorted. And it can also give us the orbital period, because this pattern is going to repeat as long as that planet is around that star. Challenges. Well, we need edge-on systems. If it's face-on, we're not going to see any away from us and then back toward us kind of motion with the star. And because it is gravitationally based and gravity falls off with distance, it favors very large, very close-in planets. Now, the last one I'm going to talk about is the transit method, and this one is definitely the king of our exoplanet detection methods. This is alone is responsible for nearly 4,000 of our currently 5,300 exoplanet detections. You're welcome. Okay. So the idea behind transit is pretty simple. You're basically looking for the dip in starlight as a planet passes in front of it. And this can happen in multi-planet systems where you're just basically seeing multiple dips added into each other if they're passing at the same time. So that's really cool. It gives us orbital period, it can give us the inclination, and it can also give us planetary radius, which is unique among exoplanet detection methods, and very important here in a minute. And it also can potentially give us the spectral information if we can watch the atmosphere through, or if we can see the starlight through the atmosphere of the planet. Challenges, it is a little bit more difficult than just, hey, let's look for a dip in starlight, because at best you're looking at like 1% of the starlight that goes missing. It's not a lot, and it gets worse the smaller the planet is. Similarly, if we have planets that are further out, we haven't had time to observe multiple transits, and so we can't really say that it's a planet. So we need a lot more time to be able to observe them, which we're getting. Tesla's a great mission. You should definitely support it. So similar challenges to radial velocity, aside from the dip in light being hard to detect. We need edge-on systems because we need the exoplanet to pass in front of it, in front of the star. And because we need it to be fairly close to the star and we need a large dip in light to be able to see it, it favors close-in large planets. Now, no exploration of an exoplanet is complete without looking with multiple methods to truly be able to characterize it. So for one thing, different detection methods have different sampling spaces within our exoplanet population. Gravitational microlensing and direct imaging both favor further out planets. Radio velocity and transit favor closer in planets. So we need to be able to use a wide range of them in order to find all possible planets. We also need to be able to constrain density in some cases, and that's not something we can easily do just with mass. So to be able to do that, we need the radius and we need the mass, which means we need transit and at least one other method that can constrain the mass decently well. Hence my lovely meme here. Yep, it's fine. So, I don't have a drink up here, sorry. And then the really cool thing is that the results from one method can actually help us guide which stars we want to look at, even if they don't tell us exactly that there's an exoplanet around that star, which is what my lovely advisor just published a paper about. This is HIP 99770b, and it was the first exoplanet detected with a combination of astrometry, which is basically take radio velocity, take out watching the spectra, and just watch the star do little daisy chains in the sky. General gist. And then it's obviously also directly imaged. And so the general idea behind the survey is to use Gaia and Hipparchus data to guide where we look for direct imaging surveys. And it's been very successful, as you can see. So overall, there's a ton of different methods. These are only the 4 most common methods used, the most successful methods used. There's a half a dozen other ones. And if you want more information, I highly recommend checking out NASA's website. They have the Exoplanet Archive, which is geared more towards scientists, but they also have a civilian equivalent of it if you are interested in checking it out. Thank you so much.
Okay. Thank you, Erica. I'm going to hold this lower. I'm learning. We're keeping it 2020 here.
Yeah.
We've got to be separated. We're finding it.
Are we?
We're going to try. All right.
You were saying? All right, that works.
So, great talk, Erica. I understand that adaptive optics is essentially magic come to life. Are there places on the Earth where we could put telescopes with adaptive optic systems to help hunt for these exoplanets?
Absolutely. So actually most direct imaging observations are done from the ground. There's a couple of different ones. Several of them are in Hawaii on Mauna Kea, including the telescope that was used for that particular image, which is the Subaru telescope. So that's Skexio and Charis, which is the adaptive imaging and imaging spectrograph on Subaru. There's also Keck and a couple other ones. All of them are in the near infrared because we can't really see exoplanets and other wavelength ranges right now.
All right, I'm trying to sort through everyone's question here. They're coming in hot. All right. Do you know what the closest exoplanet is in the habitable zone? So I guess I'm interpreting this question as one of the closer exoplanets. Like, what's the closest exoplanet we know of? Like, ballpark.
All right, I think we can stop going with the drinking word for everyone's sanity. I don't think we want to call that many cabs. Okay. The short answer is I don't know off the top of my head what the closest one in the habitable zone is, but the closest planet that I know of is actually around Proxima Centauri, if I remember correctly. So, yeah.
Okay, so is there any way to tell if the planet is edge on or face on?
Kind of. So we can basically fit models against our data and try and figure out what the inclination is. That's easier to do with like transit than some other methods. But if it's truly face on, you're not going to see it in radial velocity. You're not going to see it in transit. You could probably see it in gravitational microlensing, and you would definitely see it in direct imaging.
All right, I think we'll see. So how do you know how long it takes for a planet to come around so you can check your data for multiple passes, essentially? Also, exoplanet. Sorry.
Apparently you need to stop drinking if you're trying to hand me your phone. Okay.
It's not me, it's them.
Is it? Yeah, okay. So the question was, watching them come back around. So the short answer is you kind of don't. At least for transit, a lot of what's done is sorting through archival data, especially off Kepler. And there's a lot of machine learning that gets thrown into that to try and find where you're seeing multiple dips. Because that can be where it's like, okay, this wasn't just a weird one-off false detection, that was an actual one. I'm speaking into the microphone. I don't know what you want me to do more than that. It's kind of just a waiting game. Direct imaging, obviously, you can calculate it a little easier, but yeah.
So, long time. All right, this is a good last question. So, are there any new telescopes or technology coming out to help with this process? What's the future looking like for exoplanets?
I can't really speak for any of the detection methods outside of direct imaging, but in terms of processing data, I mean, the astrometry directed surveys is definitely a huge thing, but honestly for direct imaging, the instrumentation is a lot more of the issue than any of our post-processing at the moment. If we don't get better with that and push it into the visible range, we're not really going to get much better, or at least much lower mass detections than we're currently getting. And that's going to take 10 plus years minimum before we're even anywhere close to getting into visible and therefore like Earth mass range.
All right, so let's thank our speaker. Thank you, Erica. All right, so we have, coming up, we're going to take a short break, and then after that, we're going to have trivia, so stick around to win some prizes. Also, we have eclipse glasses. Now, I would like to make a caveat. If you come up and get a pair, you have to promise you will not lose them between now and October, and then in October, we're not going to renew it. You can't come back and get another pair for April. No, I'm kidding. We may have plenty of pairs. But yes, we have eclipse glasses up at the front. Also, if you have children, we have some coloring pages, exoplanet-themed coloring pages. Pretty fun. You don't have to be a kid. That's all color.
By the way, anyone that had questions for me from earlier, I'll be up around here. Feel free to come by and ask.
And just before we go to break and go into trivia, I just want to say, how did you guys think about the two speakers tonight? Yeah. Really, really excellent presentations. Thank you all so much. A big thank you again, of course, to Blue Star Brewery for hosting us. And our wait staff. Big round of applause, come on. All right, and we'll see who wins at trivia. Thank you, everyone.
We'll do a trivia at 8:20, and a reminder, it's not written here, but we have a team cap size of 4 per team, 4 people per team. And of course, if you are a scientist, student, undergrad, graduate, employee, you may not participate for prizes, but you can compete amongst each other. No, I never said that. No, I didn't. I never said that. I know what I say and don't say. But, bragging rights. For everybody else, we're going to be passing out trivia sheets and hopefully writing utensils. I believe we have writing utensils. If you have your own, just let us know. Yeah, we have the pens. Good. Huh? And yes, come on and get some merch here. You know, in the theme of exoplanets tonight, our top prize of the evening is going to get that cool test poster I was holding up. So that's going to be the grand prize for the evening. It's a really cool poster. I got it at a NASA conference, so it's official. And then these coloring things are really cool. There's 3 different kinds. NASA does this cool thing in their graphics department called what they call the Exoplanet Travel Bureau, which is where they make these cool posters that are like promoting these exoplanets as if they were places to go to. They're really nifty. Look them up online for the colorized one, but these are great if you got kiddos. They can color them in themselves. So we'll see you soon. So, no phones, no cheating, please. And number 2, these questions 1 through 6 are all multiple choice. Just write down the letter on the sheet. It'll make it easier for us to grade. It'll make us happy. Don't piss off the grader.
Don't do it.
Question 1. It would help if I turned it on. Question 1. Which man-made spacecraft is the furthest away from Earth? A, Pioneer 10, B, Pioneer 11, C, Voyager 2, or D, Voyager 1? Which one of these is the furthest away from Earth?
Everybody good? All right. Question 2. Charles Messier is primarily known for his work cataloging deep sky objects such as galaxies and star clusters. How many celestial bodies are listed in this catalog? A, 34, B, 110, C, 2019, or D, 72,937.
How's everybody doing on this one? Ready to move on? All right. Here's question 3. In the 1997, a great year by the way, sci-fi film Contact, Dr. Ellie Arroway receives a radio signal consisting of prime numbers from which star system? A, Sirius, B, Betelgeuse, C, Polaris, D, Vega, or E, the Sun. And a bonus, so this is not the bonus, but this is a bonus, so write it on the same line as question 3. What is the star distance to the Earth in light years? Closest answer will be given extra credit. So tiebreakers, basically. And if you haven't seen Contact, go watch it. It's a great movie. It really is.
And or read the book. It's written by Carl Sagan, and it's a beautiful, beautiful story.
Remember, the bonus for this one goes on the same line. We'll have a separate bonus question at the end, but this goes on line 3.
Everybody good? All right. Question 4. What is the name of the celestial body shown below? That one. A, the Whirlpool Galaxy. B, the Hercules Cluster. C, the Sombrero Galaxy. D, the Rosette Nebula. Or E, the Cigar Galaxy. I just want to make sure everybody knows it is that one.
This, by the way, this is a laser, not a maser. All right, everybody good? Going to move on to question 5. On January 9th, 1992, 2 radio astronomers at the Arecibo Observatory announced the discovery of the first known exoplanets orbiting what abnormal type of star? A pulsar, B, a white dwarf, C, a brown dwarf, D, a protostar, or E, a red giant. The first exoplanets discovered were orbiting around which type of star? Rare, or not rare, abnormal type star.
All right.
That was a memory recall question, by the way. It was in Erica's talk, so.
Michael's favorite questions. Everybody good? All right. Question 6. Michael, ayúdame. Here we go. What is the light travel distance to Jade's G7Z130, the most distant object known to humankind, aside from my wife? I did not write that question. Sam wrote that question.
I do not have a wife.
I'll give
Not
you all a
even close.
hint. The universe is 13.8 billion years old. Billion. Is it A, 4.6 billion years, B, 11.5 billion years, C, 13.6 billion years, D, 13.799 billion years, or E, older than the age of the universe, 14 billion years?
That joke is wife approved. Thank you very much.
All right, everybody good? We'll go to the bonus. Tonight's bonus question. Brrr. Name the top 5 highest grossing science fiction films worldwide, adjusted for inflation, in any order. Hint number 1, 2 of the films are over 35 years old. Hint number 2, superhero movies are not included. They're not science fiction, they're fantasy.
I would bet that everyone in this room can probably think of 2.
What?
I was saying everyone can think of 2. There are 2 that are very, very popular.
We'll let you simmer this one a bit, and then if you need to go back to any of the first 6 questions, just let me know. I can flash them up again. need me to go back to a previous question? If not, when you're done, you can bring it up or we'll come around and get them. And if you borrowed a writing utensil, please give them back to us, please. Thank you. Do we have everybody's? Everybody's and your writing utensil?
Please, we very much want our pens back. Please and thank you.
Thank you. Thank you. Here we go. All right, we're going to take a break so that we can grade them, and then we will give away the answers and the prizes. Good luck to everyone. All right, everyone. If I can have your attention. We will now go over the answers. So you will either be proud or shocked, or both. Question 1, which is about everyone. Woo! There we go. The first question was about which one of the spacecraft that we've launched from here is the farthest away from our planet at the moment. And the answer to that is Voyager 1. D, Voyager 1. Yes. Voyager 1 is technically outside of our solar system. It is that far away.
Question 2. I was not here for a second. Am I here? Am I here? You can hear me? Okay. Question 2. All right. How many objects were in Messier's catalog? 110. Fun fact, everybody. Charles Messier wanted to be a comet hunter. And so he set out to say, okay, all these things are not comets. And now he is most widely known for his catalog saying, these are not comets, when in fact he wanted to be a comet hunter. Fun fact for the night.
All right, question 3, which was about the movie Contact. Which star was the one that they got the signals from? And the answer to that was D, Vega. And Vega is 25 light years away from us. All right.
Question 4.
The picture of the
Oh, what was the object pictured on screen? It was the cigar galaxy.
It's elongated.
So if you ignore the red and if you look at it through a telescope, you see this white bar and it kind of resembles a cigar. So the shape kind of helped you out. It's not a cluster, it's obviously a galaxy, but hey, you learned something today.
Where's our... All right. The next question, 5, which was about the...
memory recall.
The memory recall of... Yeah, great job, me. Which was about the first exoplanets were discovered around what abnormal type of star? It was a pulsar. A pulsar. Fun little... That's
All right,
a true trivia question right there. Yeah.
And question 6, my memory recall's off. I don't know what it was. But the answer was 13.6 billion years. All right, so another fun fact for the night. In the name, you have Jades, GS, that's gobbledygook, but Z13. So astronomers use the Z scale. It's a log scale for how far something is. 13 is on a log scale, and that's freaking far, okay? Z13 is like out there. And so it would be 13.6 or 13.79. It wouldn't be older than the universe. If anybody put E, come talk to me. Oh wait, Sam has something to say.
It can't be 13.799 because that is before the recombination, so there's no light back then. There you go.
That's the trick.
And thanks to JWST, we can see things like this. You know, we can go back in time with JWST.
And now for the bonus.
The bonus are 5 movies, the 5 highest grossing movies. I saw a lot of commonalities when I was looking at the answers that y'all gave. And I would have chosen those as well, personally. But it ended up being these 5. Avatar, the original Star Wars, E.T., the extraterrestrial, Star Wars 7, The Force Awakens, and Avatar, The Way of Water.
Has anybody seen The Way of Water? It's pretty good. I don't know. Hey, don't blame the messenger, blame the box office. You all paid for these too, okay? I know most of y'all have seen at least half of these movies. And now for the winners of the night. So in third place, winning. Oh wait. Before we reveal the winners, we do have to decide the tradition of Wondergrads
Hello.
versus grads.
Yes. By the way, who was best buddies? Okay. I saw it because you put non-eligible. So thank you for your part. Thank you for your honesty. You all were in the middle, so pat on the back because you beat the undergrads, but you did not beat the wonderful grad students. So once again, grad students naturally in the process of the universe know more than undergraduate students. All is right with the world. All right.
Competition continues.
And without further ado, our third place winner of the night, which will be winning a set of these lovely solar system trading cards by NASA, a NASA sticker, and Celestron Purell.
You can't have too much. Can't have too much. All right, in third place, Yo Mama.
Come on and get your prize.
You all have to come up and claim. Represent Yo Mama. No, you're good. No. All right. And in second place,
All right, our second place winner, once again, NASA sticker, more trading cards, Celestron once again, but this time it's charging cables
in a travel case.
in a travel case.
Okay.
And
We don't
this
spare no
really,
expense.
really cool NASA poster. Oh, yeah, I'm going to need your help.
Here we go.
There we go. Okay.
Accordion style.
Look how pretty this is.
It's so black.
Sorry.
But it represents the
at
Earth
night.
and how much light pollution, or rather, how much the light of civilization has changed over the last decade. And there's a back. Why somebody would put information on the back of a poster, it boggles my mind. But I digress. In second place, Treb.
Treb?
I don't know if it's Treb or TR3B. If we're trying to play it on astronomy names.
Did we have
The
people leave
team
again?
name is TR3B.
Oh,
Treb.
that's you. Oh, woo!
Come up and claim your prize.
Sticker?
Oh, I don't have the stickers. There we go.
All right. Yay, second place.
And all the cool Celestron gear you're getting tonight is a big thanks to Robert Reeves. Round of applause for Robert. Thank you.
And the eclipse glasses.
And the things that are going to save your eyeballs when you go look at the eclipses later this year and next year. So thank
Please
you.
don't look at it with your bare eyes. Please.
All right. Our final prize of the night, the grand prize, will get this lovely test poster that, like I said, I got at a NASA conference. So
It's official.
more stickers, more trading cards, and in this box, keeping up the Celestron spirit, a Celestron tumbler for your coffee.
It's pretty nice. All right. In first place, 365 days of the, I want to say that's moon. Is it the moon or
365 days of the moon. Who are you? Oh, of course. Of course.
You get your stuff back.
Come on down. Trading cards. Those are so cool. Those are so good. There you go. Thank you. Thank you. And thank you all for coming tonight. Woo! Our next AOT, the first Wednesday of June, is June 7th. So we will see you then. Be sure to sign up for our email list and follow our socials, and make sure that if you haven't already, you tip your servers great. They always do a wonderful job. And you saw how big this room was. So a big thank you to the Blue Star and their staff for all of their help.
Thank you, everybody.
And of course, thank you to the Southwest Research Institute.